Right, so let's take a look at how one of the best ways to read an IR spectra. Now, first thing I want to highlight is what do these IR spectras look like to begin with? We kind of look at it as like a graph where there's an X and a Y axis. On the X axis is something known as wave numbers, which is the chosen unit for the absorptions that you see in an IR. And these wave numbers have a unit of inverse centimeters. And then typically on the y-axis, don't need to worry about, where this comes from, but on the y-axis is transmittance. I put that there with the capital letter T. Um, but we'll see something where, we'll have these absorptions. Sometimes they'll be strong, sometimes they'll be kind of weak. And so on. And those absorptions tell us something about the functional groups that are present in the molecule. Now, one of the important things I want to highlight right now is that it's not your job to identify every single absorption. That's impossible and a lot of times useless. It's kind of a exercise of futility. It doesn't get you anywhere. What you want to look for are the major functional group absorptions, and I will tell you which ones are going to be the most important, which ones you should memorize. So let's break down the IR spectra into regions. So the first place I tell students to look is the hydrogen region. This is anything bonded to hydrogen, it's going to show up here. And that's between 3,800 to 2,700. So that's going to be things like carbon hydrogen, nitrogen hydrogen, oxygen hydrogen. Those will be the three most common ones that you see. And if it's bonded to hydrogen, that's where you're going to see it. Now, the next region, or the next one over that you want to look at is the triple bond region. So carbon-carbon, triple bond, carbon-nitrogen, triple bond. Just kind of memorize that if it has a triple bond, it's going to show up somewhere in between there. And you should be able to like look at Hooke's law and kind of know which one will have a little bit of a higher frequency. Because remember that it's all dependent upon, or it's dependent upon the type of bond. So since they're both triple bonds, they're gonna have the same force constant. But since one has a different mass of atoms, that will affect where it shows up on the IR spectra. And then the double bond region next is around 1500 to 1800. That includes carbon-carbon double bonds, carbon-oxygen double bonds. And then anything below 1500, we call that the fingerprint region. That's also where like carbon-carbon single bonds are going to be, carbon-oxygen single bonds. We don't usually look here. Sometimes we do, but that's going to be very rare. And the reason they call it the fingerprint region is because all molecules will have a unique looking region here, much like a fingerprint. There might be a couple of similarities between similar types of functional groups like alkanes or alkenes or whatever, but they all have a unique fingerprint. So what are the important absorptions to know? Now you'll probably find a table somewhat similar to this in your textbook, and you look at this and say, oh, do I really need to memorize all of this? And no, you don't. In fact, I would commit a very few of these to memory. So let's kind of start with this is just all dealing with hydrocarbons here first. Okay. So this one here is something important to remember. This is our hydrogen region. This is an sp3 carbon hydrogen bond. So like from a typical alkane. So notice it's right below 3000. So we have our IR spectra here. And let's say, so again, we got 4000 on this end, and here's 3000. And sp3 carbon hydrogen is going to be right below that. Now, what about the other ones? You don't really care about these. We're not going to be worried about that so much. Now, how about sp2 things? Well, an sp2 carbon hydrogen has a little bit of a higher absorption. It's just past 3,000. So here's sp3 carbon hydrogen. Here's sp2 carbon hydrogen. Now, if we have an sp2 carbon hydrogen, chances are you also have a carbon-carbon double bond. So another one to memorize is this here. Notice that that is in our double bond region. So from about 16 to below 1700, and I want to highlight that, is a carbon-carbon double bond. Now, the rest of the things, again, don't worry about those. And then for an sp carbon hydrogen, so maybe we have a terminal alkyne, that's going to be around 3,300. So a little bit further. And if you have a terminal alkyne, then you pretty pretty sure that you have to have a carbon-carbon triple bond. So that's another one to memorize. And then the last category here, D, dealing with aromatic compounds or compounds that contain benzene. The carbon hydrogen bond of benzene is going to be in about the area where we'd expect for an sp2 carbon hydrogen. Because technically, these carbons here on benzene are sp2 hybridized. And let's look at some additional functional groups here. All right, so alcohols are things that contain an OH group. All right, because we have things like alcohols, and then we have things like carboxylic acids. Those tend to be very obvious. Alcohols have a pretty high absorption, and their peaks tend to be very broad. Carboxylic acid OH groups, and we'll see examples of this. So I'm going to show you some actual spectra, and we'll interpret some in a little bit. Again, kind of have this wide region where they can be found. And one of the things about carboxylic acids is their OH groups, their OH signals are even more broad. So, like if this is an example of our IR, here's like 3,000, here's 4,000. That OH for like a carboxylic acid's going to be kind of huge like this. Like it kind of obliterates the whole thing. Versus an alcohol, alcohols kind of tend to stay in their lane. They'll be broad, but they'll be a little bit more recognizable versus a carboxylic acid. Now, another set to memorize are carbon-oxygen double bonds. So all of those represent carbon-oxygen double bonds. And you can kind of see, well, there's a lot of overlap there. So how do I tell the difference between, say, a carboxylic acid and a ketone? Because there's some overlap. Well, there'd be other information that we would have. A carboxylic acid would have an OH group in its IR as well. A ketone would not have an OH group. And so there'll be more information there to kind of help us out with these differences between the carbonyls. All right, amines are going to show up in our hydrogen region. And then the carbon-nitrogen triple bond of the nitrile shows up in the carbon or in the triple bond region. So this is why I highlighted earlier how important it is to know an IR spectrum in terms of regions, because then it makes these kinds of things a lot more simple to memorize. All right, so we're going to look at quite a few IR spectra, go through the process of how we interpret it. And again, the goal is not to interpret every single signal because, as I said before, it just is a waste of time when the only thing we can get from IR is pretty much the functional group. Okay, so we're going to start with hydrocarbons, things that contain just carbon and hydrogen. So let's just start with, you know, alkanes. What do alkanes look like? Well, this is the IR spectra for hexane. And all we have really are carbon-carbon single bonds and sp3 carbon hydrogens. So if I look at the IR here, I'm going to start in my hydrogen region. Okay, so there's my hydrogen region. I got one main signal here, and that's what a typical sp3 carbon hydrogen signal looks like. And these other things here around, like 1500-ish or so are going to be our carbon-carbon single bonds. I don't really care if you label those or not because, almost, I'm going to say every, but most organic molecules have a carbon-carbon single bond in them. There are some that don't, but, you're going to see that signal over and over again. All right, so how about alkenes? So there is one hexane. Notice one hexene. We have, again, I'm going to start in my hydrogen region. There's that telltale sp3 carbon hydrogen. But notice there's something new here that wasn't there on the previous page. Just past 3000 is going to be the sp2 carbon hydrogen of the double bond. Now, if I have that sp2 carbon hydrogen, it's a pretty good bet I should have a carbon-carbon double bond. And that's what I see right there, around 1600, right where I would expect it to be. That's going to be our carbon-carbon double bond. Now you look at the rest and say, well, do I have to identify all the rest? Absolutely not. Like, again, maybe this is the carbon-carbon single bond, but what is all of this? We don't really care. That's the fingerprint region for one hexene. So it's not going to do us any good to try to go look up a table on Google and try to identify every single peak because it's not going to give us useful information. We have all the information we need by saying this IR tells us we got a carbon-carbon double bond. All right, and then finally, let's look at alkynes. What do those look like? So here we have pentyne. And alkynes are, I don't want to say tricky. You have to just kind of pay attention how do you know if you have a terminal or an internal alkyne? Because a terminal alkyne will have an sp carbon hydrogen bond, which we see right there at around 3300. And it will have the carbon-carbon triple bond in our triple bond region. Now, if we did not see, let's just pretend we didn't see this one, but we still had the carbon-carbon triple bond, we would know that that's an internal alkyne. Internal alkynes don't have hydrogens attached to them. But since we see that signal there, and we're combining that with the fact that there's a carbon-carbon triple bond, that tells us we have a terminal alkyne. Now, the other thing we have here in our hydrogen region is the sp3 carbon hydrogen, which one pentyne has plenty of. And that's where we're going to stop with this. Like we're not going to focus on all these other things. That's the fingerprint region for one pentyne, and so it doesn't do us any good to try to interpret every single signal. All right, so when we come back in the next video, we're going to look at more functional groups, and we'll also work on some practice problems.